All right. So, hi everyone and welcome. My name is Luca Caputo, and I'm a React Native developer here in Ticino. And today we're going to talk about some awesome animations with React Native. So, let's see what are the goals of today. So, first off, we're going to give an overview about what are mobile app animations and why we need them. Secondly, we're going to dive inside the actual technical aspects of the React Native implementation using React Native-reanimated library. Then we're going to explore some of the physics that power the real world physics that power the animations. Then we're going to have a live coding session, and we'll try to build an Apple Wallet inspired gallery. And then we're going to draw some conclusions out of all of this. So let's give a quick definition of what is an animation. So basically, animations are visual effects that we add to our application and to add some engagement. Morta. Sorry. Okay, so we add visual effects to our UI elements and make them more interactive and make them stand out. So the first question that comes to mind now is, do we really need animations? Are they even useful? What purpose do they serve? So in order to answer the question, we have to go over a series of key points, and we're going to talk about them one by one. So the first one is navigation. Usually when our application grows, we may add new ways of traverse the application, such as drawers, or tab bars, or stack navigators, or whatever else you can think of. And the whole navigation system can become a bit complex for the user. So how do animations help here? Let's take a look at an example here. Here we have a gallery of images. If the user taps on an image, he gets redirected to the detail of the page. And if he navigates back, the image repositions itself where it was before. So why is this useful? Well, for starters, it creates a sense of flow. When the user navigates our application, now he can see clearly where he's heading to, and when he navigates back, he immediately knows where he was before. And thus, we maybe avoid some issues like clicking twice on the same link, for example. As a consequence, this increases also the usability. As we said before, having an easy navigation makes the app easier to use. Speaking of ease of use, that's the second key point here. And let's take a look at the following example here. This is a famous dating application. This is Tinder. And you can see that we are presented with a stack of cards. Each card represents a person. And if we swipe to the right, this means that's the right decision for us. We swipe left otherwise. So why is this animation cool? Why is this useful? Well, it mimics the natural interaction. So basically, if you're presented with a real stack of cards, with a real deck of cards, and you try to put aside the first one, what happens is exactly what we saw. So the cards just move to the right or to the left. So having this bond between the actual real-world physics and an animation, it can actually increase the speed of the decision-making process. So we actually expect what is going to happen when we swipe. A third key point here is the clarity. Sometimes when we use an application or even a website, for example, we present it with a form or something that requires the user input, it's not very clear what's happening under the hood. Sometimes we may enter a wrong input, sometimes we are in a loading state, and animations here can help us. Let's see an example here. Here we have a simple login form. We have just two user inputs, and you can see that these animated figures and the inputs themselves react to the user input. So when we enter the wrong password, we get this squiggly animation here, and the images here react when the user tries to display or hide the password, and this is very nice. But what is the added value of this kind of animation? It clearly indicates error or success states. So basically, if we expect our application to give us some results about what we're doing, it's immediate. We can actually feel, OK, I made something wrong, or everything went as expected. So another use case here is sometimes, I don't know, we just try to access a list of posts, for example, and we are presented with some blank screens. Usually when we add spinners or skeletons, there are nice animation that help us understanding that the app is not broken, it's just doing something under the hood, and it just requires some patience. So last but not least, we have the premium feel. Usually, when we use an application that has really polished and well-curated UIs, we associate that with a higher quality product. If you think, for example, of the whole iOS software suite. Let's see an example here. Here we have a messaging application. This is Telegram. And you can see that we can send messages like any other messaging app, but if we send an emoji, we can tap on the emoji, and we can sprinkle some more emojis out of that. And if we try to, for example, delete a message, we get this nice disintegrating effect here. So why is this cool? Why is this nice? Because it indirectly enhances the perception of quality of our product. So as I said before, we associate a well-polished UI with a well-working application. And you may argue the same feature is implemented in many other messaging applications. We can delete messages on WhatsApp, we can send emojis on WhatsApp, or Signal, or whatever other application here, but none of them does it the way Telegram does. So we have an emotional impact, so it's delightful, it's playful, and it helps with metrics such as user retention or gamification, for example. So let's give a recap of what we saw. Why are animations helpful? First off, navigation. So we create a sense of flow. Then we have user views to reduce the cognitive load of the application here. We have clarity to provide feedback to users, clear feedbacks, and we have premium feel, so we can enhance the perception of quality. And last, they're fancy. They're very nice to look at. So now that we talked about, generally speaking, animations, let's give a high-level abstraction about what the code is going to later look like when you write an application, when you write an animation. Sorry. So the rationale here is that we have a UI element, and we want to apply some transformations here. On the left here, you can see we have a square, and we have an initial position of move 0 and rotate 0. So basically what we want to do here is apply some transformation, and we're going to move the square. So what do we do here is we define first an animatable state, the one we see between the curly braces. Once we define the animatable state, we actually need something that takes in the state and mutates the value and actually perform an animation. So we update the state with a function. But what is the actual animation? It's the way we write the function, the way we mutate the values of the animatable state. And we get a nice animation like this, for example. So as the premise of this talk, we're going to be using React Native. So let's give a quick overview or a recap about what is the framework React Native here. So React Native has two threads. One is the native thread, and one is the JavaScript thread. The native thread is reserved for the UI components, for all the native logic, and the JS thread is just used for the business logic. It's where our actual application lives. So these two threads can communicate between one another, and they do so via a bridge. A bridge is just a piece of code that serializes JSON strings and passes them through the two threads. So as you can imagine, having a bridge that just passes strings between threads is best if you run computationally expensive or UI-related logic on the native thread. So let's give now an overview about the reanimated library, which we're going to use inside of React Native to actually implement our animations. So we talked about animatable state before. And the way we define an animatable state within the context of reanimated is using shared values. Shared values are just the base building blocks. Is the 0 bit you saw before with move 0, that's a shared value. And they're called this way because they're actually shared. We write them on the JavaScript thread. They're going to actually run on the native thread. Then we have animation functions. These are the functions that actually takes in shared values, mutate them, and actually perform the animation. If we want to add some little details, for example, like delays or staggers or whatever, we can add these properties via animation modifiers, which are just higher order animations. And then we have the worklets, with just a name that Reanimated invented to define the function that we write on the JavaScript thread, but they're going to be actually run and live within the context of the native thread. So we talked about mimicking real-world physics. And that's very important for an animation to actually feel meaningful, to feel natural. So we're going to have to explore a little bit of the physics lying under the hood. But don't worry, it's going to be quick and easy, I swear. So it all starts with the harmonic oscillator. This is just a fancy name to say a spring. Okay? So the rationale here is that we have a spring, and if we apply a displacement that we're going to call x, and then release the spring, the whole system is going to experience a force. So let's translate this into a formula. And keep in mind here that our end goal is to have a series of coordinates that our object here has to traverse in order for the animation to be complete. So where do we start? We start from the definition of the Hooke's law, or the spring force. This one is, we define the force by multiplying the displacement here, x, by a constant k, which in the real world would translate to the stiffness of a spring. But then again, if we remember from our high school lectures, the force is just equal to the product between mass and acceleration. So we can substitute this formula and extract the acceleration here. But now, how do we get to the actual coordinates of the element? We have to go through the velocity now. And the velocity here introduces a new factor, which is the time. But we don't really have the concept of time inside of an application. What we do have is the frame rate. So basically, if we can imagine a 60 Hertz display, we can just divide 1 by 60, and we get 16 milliseconds. And that's our time interval. So having the time, is now we have all that we need to find the position that the element has to traverse. Let's see what the code implementation would look like. This is just a simplified example here, but we have this function we called animate, and as you can see, it takes two parameters. One is the stiffness of the spring, and the other one is the mass of the object that we want to move. So basically here, as you can see, we have hard-coded a time period of 600 frames, or 10 seconds, for the animation to run. And just as before, we just define the spring force, and from that we can extrapolate the acceleration, and then we get to the position. We take this position, push it into an array. After the loop is done, we return the array, and there we have it. You have an array of position to be traversed by the object. What is the result? This is the result. If you can see, we can tinker with the parameters here in this UI, and we get a very nice and smooth, natural-feeling animation. But there's a problem. If you recall from before, we added at a specific time frame, 10 seconds, for the animation to run. If we didn't do that, we had a problem because it would never stop. And that wouldn't happen in the real world. We expect objects to actually stop at a certain point, and to stop gracefully, too. So we have to take something else into account, which is the damping. The damping force in the real world would translate to forces like heat or friction, something that dissipates energy and eventually make all the elements stop. So how do we put this into our formulas from before? Well, we defined a new force here, which is the damping force, which is the result of the multiplication of the velocity and the new constant that we're going to be calling the damping ratio. This time, we apply the same logic as before, but this time we don't have a force, we have a sum of forces. But it's actually equal to the same formula as before, mass multiplied by acceleration. So just by substituting that, we take out the acceleration, and then we leave the rest of the formula the same. What does the code implementation look like? It looks like this. So basically, we have now the same function as before, and as you can see, we added just one parameter, which is the damping ratio. We calculate the force by, say, for damping force is equal to the multiplication of damping ratio and velocity, and then from that, the code stays exactly the same as before. So how the result would look like? It would look like this. We're adding a new parameter, and we see that this curve is now, if we tinker correctly with the parameters, eventually comes to a nice and smooth stop. So now we have all the information we need, and we are going to try to implement a real wallet, Apple Wallet-inspired gallery. Okay. So on the right here, we have our end product, which is uh, what we're going to try to build. This is an Apple Wallet-inspired gallery, so we are presented with a stack of cards, and we can scroll through the old card here, the old list here. If we tap on a specific image, we see that this one stands up on top, and the other get collapsed to the bottom. If we then tap on other collapsed card, we can switch between the card we selected and the other ones. And if we tap on the same image again, he slides back into its original position and restores the scroll. Another thing is, if we tap on this More button here, we get redirected to a new page. And this time, we have a so-called shared element transition, where the image moves itself into a new position. And as vice versa, if we try to move it back, it just has this nice interpolated animation and goes back to its original position by keeping all of the state we defined. So let's go ahead and try to build this. Okay. Morta. All right. So the first step here is to define the list. Usually, React Native comes with pre-built components, such as scroll views or flat list, but we don't really want to use them because they come packed with optimizations, such as the numbers of items to render, the initial disposition and stuff. We want to be able to have some freedom of moving elements wherever we want, exactly render what we want beforehand, and just have some navigation. So we need to implement the scroll view from scratch, but it's not very difficult. So as we can see here, we're just using what's called an animated view. Reanimated gives us this a series of pre-built components, for example, views or text or images, and we can just use them and apply animated styles out of the box. So here we're using an animated view as a wrapper for our old list. So we talked before about animatable states, so we have to define some kind of animatable state. And what do we need to track here? We need to track the user scroll, so how many pixels the user actually scrolled, and we have also to track if the user has tapped on a card, so if some kind of card is selected. So here we have two state definitions here. We have the list Y translation, as I called it, which is again a shared value. And then we have a selected index, so the card that's actually selected. And this can be null, because as you can see, we can also have no card selected, and we can free scroll the list. Then we have to react to user gesture, because as we said before, we're not using the pre-built components of React Native. We have to implement the scroll by ourselves. The way we do this is by using a new library, which is called react-native-gesture-handler. And this library gives us a pretty easy to use component, which is called a gesture detector. Sorry. And a gesture detector, what it does is just allows us to define a gesture and react to the gesture. So how do we define a gesture? That's this piece of code here. Basically, we have this builder pattern here. We take the gesture. We take when the user scroll, so it's going to be triggering an event. It's called the change event, and we're going to listen to just the vertical translation. We're going to pick this number and store it in our state. Nothing more. But then we have to have some measures in place in case the user overscrolls or just launches, for example, the scroll view. So we want the scroll view to decelerate smoothly, and we want some kind of boundaries, so we cannot go over the last card, for example. We want the scroll view to bounce back in its place, like this. So how do we do that? We apply an animation function, which is baked in React Native Reanimated. It's this with decay you see here. And with decay, what it basically does is takes in the velocity of the scroll, of the actual, so the pixel that are scrolled in a certain period of time by the user, and apply this and uses this to actually decelerate our scroll view. We also have some clamping values here, which actually defines the boundaries of our scroll view. And the way we add the bouncy effect is just with one key here, which is rubber band effect true. It's just that easy. So how do we define the actual elements of the list? So let's take a look at the list item here. Again, for what the UI is concerned, is just two elements. It's just an animated view, which again is a wrapper here, provided from reanimated, and an image. For what the state is concerned here, we have some new definitions of state. The first one is the vertical offset of the specific item. So remember, we're not moving the entire list, we're moving the specific items inside of it. And the way we do this is by creating a new piece of state, which is personal to the item, and keeping track of the user scroll input, which we pass down from the parent element, the list. We can actually calculate its stacking offset. Then we have this new piece of state here, which is previous offset, because if you recall from before, we want to be able to store the scroll state, because in case of a user taps a card, the other cards should collapse to the bottom, and the one has to stay on top, but we need a way to restore the actual scroll positions. And that's what we do here. We define another piece of state, which is the previous offset, and we store the value here. So how do we move, actually, the elements? Well, we use what's called an animated reaction. This is a function that's still provided by react-native-reanimated, and what it does, it gives us the possibility to listen to a certain change of state. You can think about this as a use effect for the native thread, or, for example, an observer, generally speaking. So what we're doing here is that we are listening for scroll values to change, and when it does change, we get to this condition here that says, okay, if no card is selected, then just position me accordingly to the scroll input, and with that, also store the scroll value, so I can restore it later. Otherwise, if something is selected, I'm going to log to the console, hey, we're not moving because something else is selected here, so we cannot actually scroll now. So this works fine. As you can see, if I tap on a card, I tapped on the first card here, I cannot scroll anymore. And if I tap on the same card again, I can now scroll. But I don't know if you noticed, but there's an issue here that we tapped on the first card, we scrolled, nothing happened, we tapped again, and we have this sudden jitter here. It moved way too fast. That's happening because we're actually still keeping track of our scroll state, even though the scroll view is not reacting to it. So what we have to do now is to disable the gesture completely when a card is selected. So we're going to do that here, the next step. OK, now that we can see, if I tap on the first card, still nothing is going to happen. The scroll is disabled. And if I tap on the same card again, then I restore the scroll normally. So what did we do here in order for this to happen? This time we add just a property to the pen gesture we defined before, which is called enabled. This intuitively means if we pass in through, the gesture is enabled, false is disabled. But the tricky part here is that we have to define this Boolean value, this piece of state, on the JavaScript thread. We cannot define it on the native thread, because otherwise this would not react. So we define it with the React way, which is this hook here, the use state. But then we need something. But then again, if you recall from before, we're changing everything. Every callback here is run on the UI thread. So we need a way to run something from the UI thread on the JavaScript thread. So we need the two contexts to communicate. How do we do that? Here we add another animated reaction here. And so again, code that runs on the UI thread. And we say, if something has been selected, so it's not null, we have to set the animation disabled. How do we do that? With this helper function here, which is called runOnJS. This is an helper that's provided by reanimated, that what it does, it takes a function, serializes it, and passes it to the JS thread, and returns a new function, which you can now pass the parameters that it expects, and actually run it. So this function here is just basically calling something from the native thread on the UI thread, which is very cool. And so we do this. We say if something is selected, disable the gesture, enable it otherwise. So what do we need to do now? We have a scrolling list. We have the tap gesture in place here. We have the locking mechanism. We have everything we need. And now we have to actually place a card on top of the others and stack all of the others to the bottom. So how do we do that? You can see here. Here we have implemented the feature. As you can see, if I tap on a card, it just gets bigger and gets on top of the others, and the other one collapses down. If I tap on another card in the stack, I can replace the image, because again, the same tap gesture as before is still in place, even though the other cards are just collapsed. And if I tap on the same image again, he slides back into his position. So how did we achieve this? Okay. It's just these 10 lines of code here. It's not a lot of code. Basically, what this does is we add another animated reaction. So we listen again for the selected index to change. And when it happens, we apply some logic here. So the first case, I'm tapping on a card, and this card is the one I'm handling right now. So it has to stack on top. You can see with Spring here is another animation function provided by react-native-reanimated. And here we can say the vertical offset here, the shared value, I want it to become 0. So basically, the shared value here stores our vertical position. We set this to 0, meaning the card stays on top. In all of the other cases, we're just saying, OK, gives some hard-coded offset here, which is 500, and decrease the stacking offsets all over the card, so collapse all of them to the bottom. If I'm tapping again on the same card, meaning that the shared value, the selected index, is now becoming null, then we have to restore the previous scrolls. And how do we do that? We store the previous scroll state in a variable, in a piece of state, and now we're just using that specific state to restore the whole scroll. That's it. That's what we need to do, and we're done this animation. As you see, also the height increases, and the way we mutate the height is by adding another piece of animation here, which is called with timing. What this function does is just animates, using a spring animation, the height of an element over a time span. If we don't pass in any parameter, like in this case, it's just going to take 300 milliseconds. But we can change whatever we want, the parameters. As you can see here, we're using damping that we saw before to say, actually increase the damping ratio and make it slow, and make it stop slower than you would do otherwise. If you mutate this, you get a bouncy effect, for example. Now we need some last steps that we have to implement here. We have to put in place some sort of navigation, right? So let's go ahead and do that. OK. What we've done here is we added this very basic more button. And if we tap on the button, we are redirected to another page with a nicely animated text and an image as a header. And you can see that we can navigate back, but it's not where it's not still the final product here. We have this weird overlapping between the same element, one in the detail page and one on the previous page. So what we did now, we actually we just implemented a new page here. This is the screen that we're going to use. The detail page is this screen here. And all of the text, the entering text, the fading effect is just this one line of code. It's an animation. It's pre-built inside react-native-reanimated. And we just say fade in, and that's it. We get an animation that works very nice. And then we have some basic layout here. We have an image. And that's basically it, nothing else. For what the actual item is concerned, we have added some very basic UI here to add a button that just redirects to the new page. That's already done here. Now we have to add the animation. We have to move an object from the page to the other and keep the interpolation flowing while we have a gesture going on. So how do we do that? you're going to see is just literally 3 lines of code. So, spoiler, what we did here is actually change the image that was here before. If you recall here, there was just an image. Now we have an animated expo image. What does it mean? Well, as I said before, reanimated comes here with some pre-built component that we can perform animation on. One of those is the animated image. But what if I don't want to use the pre-built components? What if I want to use my own? Because we have just 3 or 4 pre-built components. And what if I want to create my specific UI to animate? Well, that's very easy with reanimated. We have just this function, which is create animated component, which is just a higher order component that takes in our component and returns us the same component, this time with animation capabilities. So I can pass in whatever I want, the component I define, and this function is going to turn it into something animated right out of the box. So what we've done here is take the image here, which is not the one from reanimated, but the one from export, which I like more because I have some optimizations. It's very nice. I use it, I pass in to the function, and then I just place it here exactly as we did before, this time with a new property here, which is the shared transition tag. If you recall from before, we've called this animation a shared element transition. What does it mean? That we transition from one page to another by sharing a UI element between the pages. So this tag has to be unique, because then reanimated has to perform some calculations here and know, okay, this element is in this page, it's going to be the same element on the next page. I have to interpolate the coordinates and the dimensions of the element. So, as you can see in the detail page, we also have used the same exact component, the animated expo image, and passed in the same shared transition tag via URL parameters in this case. So, the result is here. We can click on more. We have a fully animated translation here. And if you see, if I try to navigate back, it keeps track of my animation state. And when I finish my gesture, it repositions gracefully where it was before. And that's it. These 3 lines created this, nothing else. If I tap on the same image again, we see we have all of our final product. It's built. Very few lines of code and a pretty nice looking animation. So we're now done with the coding session. Let's go back to our presentation here. Wait. OK. All right. So let's give some consideration. So let's see the pros and the cons about actually the animation. So as we saw, it helps with navigation, ease of use, clarity, premium feel, and of course, fanciness. But there's also some drawbacks of using animations. So if overused, if we put too much animations, it can feel overwhelming. Okay, the user actually may find a new user experience disrupting instead of actually pleasing. So we have to be picky. Then another concern is performance, because as you can see, we didn't add too much code, but the one we added was full of mathematical calculations and stuff. So if we kind of overlook those kind of calculations, we can actually hurt performance. So we have to be very wary where to use them. Then we have code complexity. It's not complex at all, but it's just enough for a new developer that has never done animations to actually feel a little bit confused about what's actually happening there. And last, and this is the real pain point in my opinion, is testing. Testing can be difficult, but usually, for example, reanimated or gestal handler comes packed with some of the testing utilities that you can use in testing libraries. Although, actually, we should actually test the business logic tied to the animation instead of the whole animation. We should actually delegate the test to the end-to-end tests. So let's draw our final conclusions. Animations are awesome. They can bring some additional complexities, of course, but we should definitely not be afraid of them, like this cat here, which is amazed by animations. So thanks everyone for watching. If you have any question, feel free to ask. And if you want to stop by and ask some more details about the code, I'll be happy to share. And if you want to play around with the repository, this is actually public. It's on GitHub, and you can have the code here. Thank you, everyone. Oh, sure. There you are. All right. So, is there no questions? I'll be on my way.